Concrete generates heat when it cures. That is not a flaw, it is chemistry. But when you pour 3.25 million cubic yards of it into a single structure, that chemistry becomes a threat capable of cracking the dam from the inside before it ever holds back a drop of water. That was the core problem facing the engineers at Hoover Dam. And the solution they devised was not a minor adjustment to standard practice. It was a refrigeration system buried inside the dam itself, one that had never been attempted at this scale before. Construction on Hoover Dam began in 1931, during the depths of the Great Depression. The dam sits in the Black Canyon of the Colorado River, right on the boundary between Nevada and Arizona. The project was enormous by any measure of the era, a concrete arch-gravity structure designed to tame one of the most powerful and unpredictable rivers in North America. It was dedicated by President Franklin D. Roosevelt on September 30th, 1935, completing a construction effort that involved thousands of workers and cost more than 100 lives. But before anyone could celebrate, the engineers had to solve a problem that had no real precedent. The sheer volume of concrete involved meant the dam was not simply a big version of something already understood. It was a different kind of engineering challenge entirely. Here is the chemistry that made it dangerous. When cement reacts with water during the curing process, it releases heat. For a small pour, a foundation slab, a bridge footing, that heat dissipates into the surrounding air and ground within days or weeks. The concrete cools, contracts slightly, and reaches a stable state. No problem. But for a pour the size of Hoover Dam, engineers calculated that the concrete at the core of the structure would take approximately 125 years to cool naturally. 125 years. The dam would still be hot inside when the 20th century ended. And during all that time, the uneven cooling between the interior and the outer surfaces would generate thermal stresses powerful enough to fracture the structure. A cracked dam holding back the full force of the Colorado River is not a maintenance issue, it is a catastrophe. So the question was not whether to intervene in the cooling process. The question was how. The first instinct in any large concrete pour is to break it into smaller sections, and that is exactly what the engineers did, but not in the way you might picture. Rather than pouring the dam as one continuous mass, they divided it into a series of interlocking vertical columns, each one a relatively modest block of concrete. This meant no single pour was large enough to generate catastrophic internal heat on its own. But columns alone were not enough. Adjacent columns had to eventually bond together into a monolithic structure. If each column cooled and contracted at its own pace, the joints between them would never seal properly. The dam would be a collection of adjacent blocks rather than a single unified arch. And the structural integrity of an arch-gravity dam depends on that unity. So the column strategy solved one problem and immediately created another. The engineers needed every column to reach the same stable temperature before the final grouting of the joints. And they needed that to happen on a construction schedule measured in years, not decades. The mechanism they built was elegant in concept and extraordinarily complex in execution. Before each column was poured, workers embedded a network of thin steel pipes throughout the formwork. Once the concrete was placed and the initial curing heat began to rise, cold water was pumped through those pipes continuously, drawing heat out of the concrete and carrying it away. The water itself was chilled at a refrigeration plant built specifically for the project. It circulated through mile after mile of embedded pipe, absorbing thermal energy from the curing concrete, then returned to the plant to be cooled again and sent back through the system. The loop ran continuously, column by column, as the dam rose section by section through the canyon. This was not passive cooling, it was active thermal management, a concept more familiar today in industrial manufacturing and electronics than in dam construction of the 1930s. The engineers were, in effect, treating the dam as a machine that needed to be brought to operating temperature before it could be switched on. The cost of this system went beyond dollars. It added significant complexity to an already staggering construction effort. Workers were not simply placing concrete. They were simultaneously threading pipe, monitoring water temperature, managing flow rates through a network that grew more intricate with every new layer of the dam. The refrigeration plant had to operate continuously in a desert canyon through extreme summer heat. Any failure in the cooling system risked uncontrolled temperature buildup in freshly placed concrete that could not simply be torn out and redone. More than 100 workers lost their lives during the construction of Hoover Dam. The cooling system itself was not the primary source of that toll. The most dangerous work involved the high canyon walls, the river diversion tunnels, and the sheer pace of a project driven by Depression-era urgency. But the complexity of the embedded infrastructure meant that the margin for error throughout the build was razor-thin. There is a legitimate engineering counterpoint worth examining here. The column and cooling approach was not the only theoretical solution. Some engineers of the era proposed that a different mixed design, one with lower cement content and supplementary materials, might reduce the heat of hydration enough to make the problem manageable without a full refrigeration system. Lower heat generation, the argument went, means less aggressive cooling required. That debate has continued in dam engineering for decades. Modern large concrete dams do use low-heat cement formulations and careful mix design as primary tools. But for Hoover Dam, given the timeline, the scale, and the state of materials science in 1931, the embedded pipe cooling system was the approach the engineers committed to, and the dam's structural record since its completion suggests the decision held. Hoover Dam was dedicated in 1935 and has been in continuous operation since. It remains one of the largest hydroelectric facilities in the United States. The Colorado River is held back by a structure that was poured in columns, cooled by circulating refrigerated water, and grouted into a unified arch only after each section reached thermal equilibrium. The 125-year natural cooling timeline was compressed to a construction schedule measured in a few years. The concrete inside the dam is now fully cured and stable, no longer generating heat, no longer contracting. The pipe network embedded in the columns is no longer carrying chilled water. In some sections, those pipes were eventually grouted in place and became part of the structure itself. The cooling system that made the dam possible is now permanently entombed inside it. What Hoover Dam demonstrated is that scale does not just magnify engineering problems, it transforms them into entirely different categories of problem. The chemistry of curing concrete was well understood in 1931. What was not understood until engineers were forced to confront it directly was what that same chemistry does when you multiply the volume by a factor that eliminates every natural cooling pathway. The answer required inventing a solution that had no real precedent, building it in a remote desert canyon during an economic crisis, and trusting it to work before the structure could be tested under full load. The dam held, the cooling worked, and the embedded pipe system that made it possible quietly became the template for large concrete dam construction for the rest of the 20th century. Not celebrated, not visible, but load-bearing in the most fundamental sense. Visual reconstructions are illustrative. Facts and interpretations are based on the sources listed in the description.